Hey everybody, in this video I'm going to do a quick review of logarithms for those of you who want a little brushing up on various logarithm skills. On the first slide in this video I'm going to talk about the graphs of them and general properties of logarithms and exponents and their inverse nature of the two. On the second slide I'll do some mentally evaluating and expanding and condensing. I'm going to make another quick video on logarithms, and that will be on solving them. So let's talk about graphing logarithms first. You should know what the general shape of any logarithmic graph is, no matter what the base is. Also, keep in mind that for a logarithm, the basic way to write it is y equals log base b of x. B is the base. It can be any number. However, if the base is 10, that is the common log. And if the base is e, that is the natural logarithm. Those are the most commonly used logarithms in applications and also in calculus. So in order to graph a logarithm, the easiest way is to think about what the graph of the exponent looks like, or the corresponding exponential function. The reason this works is because logarithms and exponents are inverses of one another. That means they undo each other, so whatever one function does, the other undoes. They have the same exact shape, but they are reflections of one another over this line y equals x, and that is the diagonal line, a 45-degree angle, like that. And the graph of an exponential, like 10 to the x and its logarithm, log base 10 of x, they have the same ordered pairs, but the x and y are reversed. Notice right here, I'm going to try and graph y equals log of x first. I didn't put a base here. That's because it's understood if you omit the base that the base is 10. So I'm going to go ahead and assume that b is 10 there. And I graphed 10 to the x already here. I noticed it was exponentially increasing. It's a very steep increase right here. It also has a horizontal asymptote of y equals 0. So let's take the three ordered pairs I have here and reverse them, and we'll get the graph of our logarithm. So I had the ordered pair 0, 1, meaning I'll have the ordered pair 1, 0. I had the ordered pair 1, 10, meaning I'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1. And I had the ordered pair negative 1, 1/10, or 0.1. So that means I'll have 1/10 or 0.1, negative 1, right there. And if I connect these, let me try that again. This isn't perfect here, but it's very, very slowly increasing. It almost looks like it levels off, but it doesn't level off. It's still going to increase slightly. This is supposed to get closer and closer to what is now a vertical asymptote of x equals 0. So again, x and y reverse here for the asymptotes as well. Let's do natural log of x. So here I don't have a base again, but because it's ln, that means natural log, so that means the base is e. So that means it's the inverse of e to the x. I already graphed e to the x right here. I'm going to go ahead and reverse my ordered pairs and get the inverses graph. So right here I had the point 0, 1. In fact, every exponential graph will have this point unless you shift it up, down, left, or right. So I'm going to go ahead and graph 1, 0. Here I had the ordered pair 1, e. Now you have to remember that e is just an irrational number. It's like pi. It's a constant, 2.71828. So instead of having 1, e, I'm going to have e, 1. So let's go over 1, 2, 2.7, 1. And here I had the ordered pair negative 1, 1 over e, but that's kind of a weird thing to look at. I don't really know what that is off the top of my head. It's 0.368. So that means I'm going to have 0.368 negative 1. Again, I have a vertical asymptote that it's going to level off at. And here's my vertical asymptote, x equals 0. There's my vertical asymptote. So moving on here. Basics of logarithms. You need to know how to mentally evaluate these. And remember, in order to mentally evaluate, just think exponents. because they're inverses. To mentally evaluate a logarithm, let's do this one. You want to think, what exponent should I give my base in order to get this number here? So I have log base 5 of 25. What exponent do I need to give 5 to get 25? Well, you need an exponent of 2, because 5 squared is 25. How about this one here? Log of 100. You might be thinking, well, there's no base there. But remember, it's understood to be base 10. It's the common log. So what base do you give 10 to get 100? 2. How about this one? Log base 25 of 5. So here we reverse the two numbers. What exponent do you give 25 to get 5? This one's a little bit different. To go from 25 to 5, what you really need to do is square root it. And then if you remember, square rooting is the same as raising something to the 1/2 power. So 25 to the 1/2 is 5. Here, 5 to what power is 1 over 25? The answer is -2. 5 to the -2nd. Anytime there's a negative exponent, in order to make it positive, you do 1 over the same expression, but the exponent's positive, which is now 1 over 25. Log base 2 of 32. 2 to what power is 32? We have 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. That is a 5 right there. And last one, I skipped this one here. Natural log of e to the 4th. This is not the base. The base is down here. I didn't even write it. So you need to think, what exponent do you give e to get e to the 4th? Well, give it an exponent of 4. Some properties to remember for all logarithms. Oh boy. Come on. Hold on. Okay, some properties to keep in mind for all logarithms. Sorry about that, computer issues. Anyway, properties for every logarithm. So we have log base b. Oh my god. Okay, let's try this again. Properties for any logarithm. Log base b of 0 is 1. No matter what this base is here, you would think, okay, what exponent do I give the base to get 1? You would always give it 0, because anything to the 0 power is 1. Log base b of 0 equals, it doesn't exist. You cannot give something an exponent and end up with 0. Also, you can't give a logarithm an input of 0, because if you look at this graph, here are logarithmic graphs, this one and this one. You can't give it an input of 0 because there's an asymptote right there. The next two properties have to do with the inverse nature of logarithms and exponents. These will be used quite a bit. If I have a logarithm base b and I raise it to b to the x, those two will cancel, leaving me with x. So for example, if you have log base 4 of 4 to the 6x, let's say, the logarithm's base is the same as the exponential's base, so that means they cancel, leaving you with 6x. And here, if I have b raised to the log base b of x power, again, they cancel if the bases are the same, leaving you with x. An example of that would be like e to the natural log of x plus 4. And remember, natural log has a base of e, so the base of the exponent and the base of the logarithm are the same. They cancel, leaving you with whatever you were doing the logarithm of, x plus 4. A couple properties that you help out whenever we're trying to simplify, or so expanding or condensing. If you have log of two numbers multiplied, in order to expand, you would give each its own logarithm and add these numbers, or give each number a logarithm and then add the two. Here, if you have a logarithm of two or more things divided, you're going to subtract the two logarithms. You give each term its own logarithm. And here, if you have log of a to the n, what you do is, oh, it's not letting me right there. You bring the exponent out front, and the n is right here, and you multiply it by the logarithm. And a quick example of that is, let's say I have log base 7 of 49 plus log base 7 of x plus 1/2 times the quantity log base 7 of z plus log base 7 of y. Right here, I don't have any variables. I just have log base 7 of 49. I can evaluate that. And the answer is 2, because you give 7 an exponent of 2 to get to 49. And I have log base 7 of x here. Now, there's two ways to do this. You could either distribute the 1/2 to each logarithm, or you could start on the inside and condense. I'm going to start on the inside. So that means I still have 1/2 here times quantity log base 7 of. Notice the bases are the same here. And I'm adding log base 7 of z plus log base 7 of y. So that means I can take the two logarithms and I can multiply z and y. See if I can, I need a new page here. So I have 2 plus log base 7x plus 1/2 log base 7 of z, y. What I'm going to do next is, so I have log base 7 of z, y. Anytime you have a coefficient out front and you're trying to condense, what you can do, or what you need to do, is bring that coefficient up top to be an exponent. And whenever we are condensing, you don't want fractional exponents. You want to go to radicals if possible. And raising something to the 1/2 power means taking the square root of it. So I have 2 plus log base 7 of x plus log base 7 of the square root of z times y. And one last thing here, I have log base 7 of x plus log base 7 of square root of zy. Because the bases are the same, what I can do is multiply the 2, but the x can never go under the square root. And the 2 is just kind of up front there.